Hi, hello, hi. So I want to do the last section of the year. So there's always some excitement in coming to coming to the end. And the last section, it differs from the previous sections in two ways. The first is that there won't be any confidence intervals here, only hypothesis tests. So that's a little different. And then the second way that it differs is that it's a different setting, just like we had the different settings in chapter 6. And as a result, we have to go to a different place on StatKey. So most of what I'll be talking about today is simply showing you how to use the different place on StatKey. In particular, much of it will be exactly the same. All of the hypothesis test reasoning will all be exactly the same. So I'm trying to emphasize the unity rather than the differences. Okay, so let me start in on the material. So this section 7.1, and this the book calls it chi squared. Chi is a Greek letter, chi squared, and so I want to put the setting in here. We often worked in the past, for example, in section 6.2, and also some of the earlier sections. We often worked in the past with proportions. So here's an example of you might have men and women, you might have treatment group and control group, and in those cases, we end up with two proportions. Here's a study, for example, we want to test what percentage of people have a reaction to a drug, and we want to see the effect of gender. So we give the drug to people, and we find that 45% of the people who have a reaction to the drug are men, 55 are women. So we call p hat 0.45. And we might find a confidence interval. We certainly did that in section 6.2, or we might run, section 6.1, or we might run a hypothesis test, p equals 0.5 against p is less than 0.5, all very routine from section 6.1. The point here is that if men are 45%, then women must be 55%. That is to say, if there's two categories, then from the one proportion, you automatically know the other proportion. You might remember the formula p hat times 1 minus p hat. That is, you use the two numbers, and there's only two numbers. If you know the one, you can figure out the other by taking 1 minus. What if there's more than two categories? What if there's 3 categories, 4 categories, 5 categories? What if you didn't have just men and women, but men under 30, men over 30, women under 30, women over 30? What if you had more than two categories? What do you do? Okay, and the answer is you do today's section, at least what we're starting in on today's section. So this is called Chisquare Goodness of Fit. And I'm going to take an example from the book because that way it saves a person having to enter the data. So the example is rock, paper, scissors, and I imagine everybody in the room has some idea how to play rock, paper, scissors. There's 3 categories, rock and paper and scissors, that's all, 3 categories. And obviously if your opponent can guess which things you're going to do, then they have they have an advantage over you. So a study looked at 119 different people and reported what they played first. Rock was 66 of the people, paper was 39 of the people, scissors was 14 of the people. Now, if you don't know anything, then you might say that probably it would be 1/3, 1/3, 1/3, but this is a little different than 1/3, 1/3, 1/3. In particular, scissors seems underrepresented and rock seems overrepresented. So we have a hypothesis test then. A person who doesn't has no prejudice would say, well, I expect them to be 1/3, 1/3, 1/3. I expect that if you had not 119 players but 100,000 players, that if you did a census, you'd find that the true number was 1/3, 1/3, 1/3, and that you got something different than 1/3, 1/3, 1/3 only because you did a sample instead of a census. And that's the usual reasoning of a null hypothesis person. HA is to say, no, not that. That 66, 39, 14 is symptomatic that 1/3, 1/3 is just simply not right. So HA is that there's some other P. It might be that P rock is 1/3, but maybe P paper is different and P scissors is different. So it's just not 1/3, 1/3, 1/3. It's something else. So H naught is, in this particular example, is that all 3 are the same. HA is that it isn't what it is on the previous line. We'll see an example in a minute where these 3 are not all the same. You can make them be different numbers as long as they add to 100%. But HA is always going to be that they're not the same. They're not what it says on the previous line. Okay, so in order to do this, then, the way you do a hypothesis test is always the same thing. You always assume H naught. In this case, we'll assume 1/3, 1/3, 1/3. Then you've got to calculate how far is your sample from the predicted value, and if your sample is way far off, if your sample has a tiny, tiny p-value, if your sample is way far off, then you reject H naught. If your sample is perfectly everyday, if your p-value is 20% or 30%, if your sample is perfectly everyday, why then you fail to reject H naught. So when we were doing hypothesis tests earlier, we had to figure out the z-score of our sample, or we had to figure out the t-score of our sample. It's just some formula, and we just simply applied the formula, and then we had to take that z-score or t-score and look it up somewhere on StatKey. Exactly the same thing. In this particular case, we're looking up, that's not called a z-score or t-score, it's called a chi-squared number. So it's just a number, some formula that we have to figure out. I don't like to pull these things like out of a hat and just tell you, I'm not going to give you the answer. I'm just going to show you where to find the numbers. So I want to give a person some idea where these numbers come from. But really, we're mostly interested in the chi-squared number is the cold truth. Okay, so but for some idea where it comes from, if it were really 1/3, 1/3, 1/3, then the 119 people should be 1/3 of 119. That turns out to be 39.7. 1/3 of 119 turns out to be 1/3 of 119. So it should be not 66, 39, 14, but ideally it's 39.7, 39.7, and 39.7. Those are called the expected counts. Each of the three is called a cell. Those are called the 39.7s are called the expected counts here. And in order to calculate how far is the sample that we got from the expected count, a person does this formula. And again, we don't do the derivations of these things, but I want to give a person who leaves this class some idea that this stuff doesn't just come out of nowhere. This is not the world's simplest formula, but it's not the world's most complicated either. Observed minus expected over expected. So you take 66 minus 39.7, square it, and divide it by 39.7, and if I did the calculation right, you get 17.48. 39 minus 39.7, square it, divide it by 39.7. 14 minus 39.7, square it, divided by 39.7. So I think that those three numbers, are right. When you add them up, the 17 plus the 0 plus the 16, you get 34.101. That's the analog of the z-score or the t-score. That's the number we're going to look up on the appropriate place on StatKey. So you have to calculate that value. The honest truth is we're going to get StatKey to calculate that value. You have to calculate that value and look it up somewhere on StatKey. So this is just exactly like every other hypothesis test that we've done, meaning that you write down a hypothesis. You figure that if your sample is close to the expected value, then you'll just consider it fail to reject. If your sample is far from the expected value, you'll say reject. Okay, so I want to take you to StatKey. It's time to take you to StatKey. Oops, in the wrong place on StatKey. So let me bring this up. There we go. There's StatKey. Okay, so new chapter. Time to find a new place on StatKey, and there it is down there. See, Goodness of Fit. Having a little trouble manipulating these things on the window. See it down there, Goodness of Fit? That's what I want because this section 7.1 is called chi-squared. That's a Greek letter chi. Chi-squared Goodness of Fit. So you click on that. And I told you I selected an example from the book because I just want to save us the trouble of entering the data, which is pretty much a yawner. So there's rock, paper, scissors up there. So the locks have already entered this data for me. I don't have to do it. But if the locks hadn't entered the data, I would simply click on Edit Data and enter it myself, and it's not brain surgery. There's rock, there's paper, there's scissors. Okay, but the locks have already entered it for me, so I won't bother. The null hypothesis comes next. Remember, it was 1/3, 1/3, 1/3. So I click on the null hypothesis, and they've already entered for me 1/3, 1/3, 1/3. There's a little rounding thing with the number 4 over there. But anyway, it's 1/3, 1/3, 1/3. And then StatKey will use that to calculate this 34.101 number. It's a little small. Can you see it up there, 34.101? I'm not even sure if you can see it. Oh, you can see it, 34.101. Before I leave this screen, though, having gotten the 34.101, which was the number I came to the screen for, before I leave this screen, this is a randomization screen like we saw in Chapter 3 and Chapter 4. So I just want to give you some idea. We know what the z-curve looks like. We know what the t-curve looks like. So what does the curve look like here? So just to give you some dim idea of what's happening, again, just to make it seem so that it isn't magic, I'm going to generate 1,000 samples. And what you see is that things close to 1/3, 1/3 kind of fall off. That there are samples close to 1/3, 1/3, 1/3. What was that? 39.7, 39.7, 39.7. So I put my mouse over one of the samples here that's pretty close by, and you see it's 37, 43, 39. That's pretty close to 39.7, 39.7, 39.7. And here's another close by one. It's 45, 36, 38. Pretty close. So they end up with a small score, a chi-squared that's small. But these guys out here, they're further. They end up with a chi-squared that's big. This is exactly like a z-score, exactly like a t-score. Okay, so the curve is falls off sharply like that. So that's going to be the chi-squared curve when I get to that place on StatKey. I got to remember the number, though, 34.101 for when I go there. All right, back we go. I'm just like I looked up the z-score here and the t-score here. Now I'm looking up the chi-squared score, so I'm in theoretical distributions chi-squared. Degrees of freedom is going to be you take the number of categories. There was rock, paper, scissors. That's 3 categories. So you take the number of categories and you just subtract 1. So 2. And you see that curve that looks a little bit like the one from the previous screen that falls off rapidly. Chi-square scores that are small are in here. Chi-square scores that are large are in here. And a person sees right away 34.101 is not even on the screen. It's literally off the charts. 34.101 is basically impossible. It's like having, a z-score of 18. I mean, it basically can't happen. But I'll go through the motions anyway. You click on right tail. You enter 34.101, 34.101, good, and it says 3.9 E minus 8. That's scientific notation. Remember what minus 8 means in scientific notation? It means there's 7 zeros and then a 3 9. So point 0.0000000 and then 3 9. I mean, the difference between that and nothing. Come on, this is a practical class. That's basically 0. So we had an observation, 66, whatever it was. Our observation for rock, paper, scissors had basically a 0% chance of happening. So just as always in a hypothesis test, if the null hypothesis people look at the observation and say it had basically a 0% chance of happening under their assumptions, then they say, I guess my assumptions were mistaken. I guess 1/3, 1/3, 1/3 wasn't right. I guess it must be something else. That is to say, reject H0. Low p-value means reject H0. We got a tremendously low p-value, almost 0, so we reject H0. Okay, let me bring StatKey down and go back to the slides here. Oh, I can't find them. There they are. Back to the slides. So we got a chi-squared value of 34.101. We went to the screen here that gave me the 34.101, and that screen, in fact, will give you all the numbers if you're interested in looking at the accounting of where the numbers come from. And you do the hypothesis test. The degrees of freedom is the number of categories. That's 3 categories: rock, paper, scissors, minus 1. You look up 34.101 on the graph in the way that I did. I like to freeze the screenshot into the slide. Just I think it helps make it easier for a person who's trying to figure out what's happening for it to be frozen instead of trying to stop the video. And we got essentially 0 for a p-value, so we of course reject H0. Okay. So again, we started by discussing the case where there are 2 categories. If there are 2 categories, then knowing the men automatically gave you the women. You could do a chi-square test in 2 categories and you get to the same conclusion, but the formulas in section 6.1 are just simply easier. Now, the second point is we did a case with 3 proportions, 1/3, 1/3, 1/3. And in a minute, we're going to go to a case where there are proportions, where there are more than 2, but 3 proportions, where they aren't all equal. Okay, so where they aren't all equal, just to show what you do, and you won't be surprised to hear that you go into StatKey and you enter something slightly different in StatKey. That's all there is to it. Okay, so here's the example. A company designs a pay increase plan that has 3 categories: merit, inflation, and no raise at all. The target is supposed to be a quarter of employees get merit raises, 65 of employees get a nominal inflation-linked raise, and the remaining 10% get no raise. So what happens at the end of the year, then the company looks and sees what percentage of employees actually got merit raises, what percentage of employees actually got inflation-linked raises, and what percentage of employees actually got no raise, and they try to see, are we close to the target of 25, 65, 10, or are we actually far from it? So because of year-to-year variation, you don't expect the numbers to come out exactly 25, 65, 10. You expect there will be some small difference, but you want to know, when you look at the actual data, you want to know, is the actual data close enough that we can call it just a sampling thing, or is the actual data so different that we say to ourselves, this is not a sampling thing, there's something else going on. So here it is. The proportions are 25, 65, 10. That's H naught, the nominal values. HA is that it's something else. And we're going to use alpha equals 0.1. So this is a very typical hypothesis test. The only difference is that instead of there being two categories, two proportions, one of which you can calculate from the other, there are three categories. That's all. Okay, so three categories, and I could go to stat key, and I will go to stat key with the 25, 65, 10, and get stat key to calculate that value. So here I go, bring up stat key, and it's still, of course, where I left it a minute ago. Oops, I didn't bring up stat key, I brought up something else. I bring up stat key, there we go. It's still there, I left it a minute ago, so I got to go back to chi-square goodness of fit. That's how I'm going to calculate chi-squared. It was 25, 65, 10, wasn't it? Come on. 25, 25, 65, 65, 10. 10%. So 0.10. Okay, and that adds to 100%, so I think the thing should not argue with me. Okay, I have to enter the actual data. I'll enter the actual data in just a minute when I go to the slide to enter the actual data. So I'll edit that section in just a second. And then over here will be the chi-squared number that I want. Okay. So first thing to do is to enter the null hypothesis, and I entered that just a second ago. I'm having trouble manipulating all the windows. Here we go. I entered 25, 65, 10. We saw that just a minute ago. And then I gotta figure out what are the actual numbers. So the actual numbers are in this screen. The actual numbers are 193, 365, 42. 193, 365, 42. 193, 365, 42. 193, 365, 42. Come on, come on. Having a little trouble here. There we go. 190, oh, I forgot already. 193, 365, 42. 193, 193, 365, 365, 365, 42. 42. Okay, and stat key wants me to give these names, so fine. So this is merit, inflation, and no raise, none. Okay. Okay, looks like I did that right. 193, 365, 42. And up there is the chi-squared number 261.190. So that's exactly like the z-score or the t-score. I'm just simply going to punch that fella in, 261.190. Okay, so again, the null hypothesis, I entered that first. Ah, it went away. Oh, darn it all. Darn this thing. 65, 65. No, it was 25, 65, 10. 25, 25, 65, 10. There we go. No. Not having very good luck today. 25, it's a good thing it's the end of the semester. 25, come on, come on, come on. You're not helping me out here. 25, 65, 10. 65, and then 10, 10, 10. There we go. 10%, good. Okay. So I think it's 25, 65, 10, but I better click on it and make sure, yes, 25, 65, 10, okay? and 193, 365, 42. So that's what I thought it should be. Now so this chi-squared looks more reasonable. Okay, so chi-squared is 19.330. So that's a more reasonable number. I'm going to go to the chi-squared part of stat key, and I'm going to enter 19.330, and it's going to tell me how likely is a 19.330. So just like the z-score, just like the t-score. So back I go to the chi-squared section, and I'm going to say degrees of freedom is 2 because there are 3 categories, and I'm entering here 19.330. 19.330. Hope I did it right. There we go. And it again says practically 0. How many zeros are there? 1, 2, 3, 4. 4 zeros and a 6, 3. So the p-value is basically 0. A p-value of basically 0. Okay, back to the slide. Here we go. Yes. Okay. The p-value is 4 zeros and a 6, 3. That's way below 1%. Way below alpha equals 0.1. So we reject H0. So the p-value is very small. With an alpha of 0.1, we reject H0. So it's basically not possible to have seen this. Just like the earlier sample, it's basically not possible to have seen this sample, and so we reject H0. Oops, excuse me, I clicked one too far. Okay, so just like the previous example, there are in this case 3 categories, 1, 2, 3 categories. That's why I entered degrees of freedom equals 2. The only difference is that in the null hypothesis, the 3 proportions are simply different numbers. That's all. This problem is exactly like the previous one, except it's harder to enter because I had to type the data in, and then I entered 3 different, for the null hypothesis, entered 3 different proportions that of course have to add to 100%, but they're just different. When we calculated, what we had to calculate was the chi-squared value, calculated the chi-squared value of 19.330, and I used that Chisquare Goodness of Fit screen to do it. And then next I entered 19.330 into the chi-squared section of stat key with degrees of freedom 2, and it told me the p-value. So as always in a hypothesis test, you assume the H0 people are right, and you see how far off is our sample, and our sample proves to be pretty far off. The p-value is quite low, so low that it's below alpha, and so we reject H0. Okay, very good. Okay, very good. The last one, and I'll post the homework videos in not too long, and we'll see.